Okay, so good evening, everyone, and welcome to this online version of the Asset Colloquium. For those of you who are not from TIFR and who may not be knowing what ASSET is and what it stands for, ASSET stands for Advances in Science, Engineering, and Technology. So this is essentially a forum which organizes a colloquia like what you are part of today at 4 p.m. on all working Fridays. The ASSET colloquium had a different name to begin with, but it was started by some of my colleagues way back in 1983. And since then, it essentially organizes colloquia on matters related to engineering and technology, the detectors, electronics, instrumentation, and also a few topics which are areas which are not covered, let us say, in the other colloquia. So TIFR also organizes natural sciences colloquia, NSF, it's called Natural Sciences Faculty on Wednesdays, and also maths colloquia on Thursdays. So ASSET is a complementary colloquia to the rest of the two. So this is the history of ASSET. And today we are going to have a colloquium that is going to be given by Professor Ashok Kumar from Delhi University, and he is going to talk on GEMS. GEMS, of course, he will tell you the type of high energy particle physics detectors, and in the context of CMS experiment, the developments that he and his colleagues are involved, both at the CMS experiment at Geneva and also lots of development that they have successfully part of in the Delhi University and context in India. So to say a couple of words about today's speaker, of course, Ashok Kumar, we all call him Ashok. He is so well known to all of us and also in particular to TIFR because during his days of PhD at Punjab University, where he actually joined, he completed in 2007, his work was involved in the development of the so-called HCAL detector modules for the CMS experiment. And lots of years together, he and his other co-student actually spent time in TIFR. So he's a very well-known person to TIFR. He joined after PhD Delhi University the very next year in 2008, where he is currently an assistant professor. And his research fields in in terms of physics interests are Higgs and its exotic decays. And his also specialty is more as is going to speak today on, is relevant detector instrumentation. Currently is involved in developing gem detectors for the CMS experiment at Large Hadron Collider, that is LHC. The Delhi University has successfully fabricated and delivered very good quality, large-sized gem detectors. Under his leadership, he is the production site manager responsible for all the production and very stringent quality control of these detectors, about which I'm sure he's going to talk. And what is also is that he also initiated indigenously developing and qualifying large size gem foils, which are the main components that are required for the detectors using local industry in India. So this is very nice thing to kind of to note, while it is true that many of us work in experiments elsewhere, but it's also important to bring this technical know-how and expertise to India, to our own labs, and even more important is to kind of spin off them to the local industry and also train the younger students who are going to take up bigger roles in future. To that extent, I think Ashok and his team have been doing wonderful work. So with these few words, I now invite Ashok to start his colloquium.
Thank you. It is an honor that we have listened so many colloquium at TIFR, but now we are presenting to the audience the work we are doing right now. And in today's talk, I will discuss about GEMS, basically gas electron multipliers, a new hybrid detector for the for the many experiments actually. And whatever techniques we have applied here had been learned at TFR also. So we were lucky that we were trained there. There are excellent people around. And we have not only worked for uh, uh, GEMS, we have worked for HCAL sensors before, HCAL modules. We have worked for ECAL sensors, silicon sensors from Delhi University. And now we are in the GEMS for CMS experiment. So we need detectors and the relevant instrumentation to do physics at CMS experiment at Large Hadron Collider. This is our prime responsibility. We have to do this job to train the people, to train the young people, and also to commit our, commitment, the actual commitment to the experiment. Okay, with these words, I will just start with my first slide. You can see a very nice, stamp size picture, the Indian miniature. I noticed that in 2015, some Belaso, another person named Belaso, has shown in some conference. So he has, gathered this image, very old image, using the GEMS. So he has applied some elemental technique to, like XRF we do. So he has done the job using the GEMS. And I don't know why he did this with the Indian pictures, but this was in the literature. So we can do wonderful applications using GEMS. And this is the one of the thing when I was searching through literature, old literature, I found in 2015 conference, the person has presented. Okay. The outline of the talk is that we are using GEMS in CMS. So what is the motivation we have? And in CMS, we are going to upgrade in 3 major stations, G11, G21, ME0. So these are GEM and CAP station 1 and layer 1. And similarly, layer 2 as station 2 and layer 1. And there is ME0, which is the end cap layer 0. I will discuss about techniques about the fabrication and the quality control. And then the production using the local industry, basically the Micropack Bengaluru. And we have produced small and large size foils. And then I will discuss about applications we can do using these GEMS, and in particular what we are doing at Delhi University. Okay, we know that Nobel Prize in 2013 was given to Higgs and Englert for discovering by Higgs Higgs particle at Large Hadron Collider. So in this discovery, if we go to year 2012, we see that there is a very nice plot of the events which went into the Higgs discovery. Now, if you see, I have only few events, 3 events, 2 events. If we total them up, 6, 7 events. And these events are containing muons. And these muons are detected using the muon detectors. So muon detectors are crucial for any high energy experiment, the collider experiment, also to the non-collider experiments. But at CMS experiment, this is the crucial part of the CMS experiment for any discovery you do. So if you see, this is the one of the event which went into this plot. So we have a muons coming from the Higgs decays. Higgs decays to jet particles, and jet particles decays to 2 muons. So if you have 2 jet particles, the 4 muons will come out from the buttocks. So we have these stations are the detectors, the muon detectors. You have RPCs, you have drift tubes, you have CSCs. So gaseous detectors based upon ionization detectors are muon detectors in this case. So muon detectors are important for CMS experiment, also for other experiments, ALICE or ATLAS, any experiment you take. I am showing an example. So this is a discovery event which has, particle coming from discovered through the using the muon detectors. Okay, so in the nuclear and high energy physics experiments, gaseous detectors are in use since 1906 when Giger and Rutherford started, discovering things, and they started using ionization counters, proportional counters, and in 1928, Giger and Muller came up with the idea of Giger-Muller counter, and in our training labs, master's labs, bachelor labs, we use these Geiger-Müller counters so often. Now, ionization properties provide perfect means of tracking charged particles in large gas volumes. So a particle is interacting, ionizing particle is interacting through the gaseous medium, and we have ionization, and that ionization medium is the sole criteria to see the interaction, to see the particle. So the particle is losing energy through the ionization. Gaseous detectors provide tracking accuracy with the spatial resolution of order of 100 microns. This is an excellent thing which is happening with the gaseous detectors, that up to the micron size spatial resolution we can get. And the timing resolution is always better. This is in few nanoseconds. Gaseous detectors are less expensive as compared to silicon detectors or other detectors in the field, and you can build large volumes using these detectors. So typically we hear about proportional counters, drift chambers, cathode strip chambers, the TPCs, the RPCs, as we have in INO also, the microstrip gaseous detectors, the GEMS I'm talking about, the other class of GEMS, micro megas. So these two categories are based upon, one are the wired counters, another one are the wireless counters. The wireless counters are based upon the based upon the PCB technologies, the printed circuit board technologies, and also the fabrication techniques involves the photolithographic and etching techniques. So the principle of working is very simple. A particle ionizes the medium, the gaseous medium, which whatever we have chosen, it ionizes and produces some interaction. The second step should be that primary electrons which are produced after the ionization are energetic enough to ionize the other molecules, and then a complete envelope of charged particle is produced. We have electrons and ions. This is called as the avalanche effect. The electrons are collected at the anode, ions are collected at the cathode. So a complete effect is happening in the presence of the potential difference or electric field we have. So this is the basic of any gaseous counter we see around us. In an informed field, the motion of electrons and ions is governed by the acceleration and collision with the gas molecules. Motion with the uniform velocity depends upon the intensity of electric field which we have applied here, and the properties of the gases which we are using. Electrons move faster, they have more drift, and ions are slower because they have more mass. And this was also said by Rutherford and Geiger that Townsend was working not only on ionization but also on the principles by which you can get more output in the charge. So there was ions produced by collisions with the neutral gas, so you have more charge coming in the interaction. So not only that you have a primary ionization, but the secondary effects are more important for any discoveries in the future. So these detectors suffers a lot due to the aging and discharges. We have many gases involved in these gaseous medium, gaseous detectors. So in the passage of time, when we have more interactions, then in the presence of more fluxes, the gases interact with the gases interact in the presence of gases. You have the plasma happening at very high fluxes, lot of temperature, high pressure gases are there. So there are deposits of these plasmas on the detector electrodes, and similar effects are seen in the wire counters. So with the passage of time, these detectors dies out. In the LSC environment, where we have a lot of radiation, very harsh environment, these effects are going to be crucial to choose any detector technology. So if you see that there are so many polymerization of organic compounds which are forming deposits on wires and also on strips, as I have shown in the earlier slide. So if you see the same images of these detectors, with the time their surface goes bad, and there are the field changes will occur, and with these field changes the discharges will happen. There are many effects, Multer effect, and many effects happen. So whenever we have to choose any detector for Large Hadron Collider, we have to think of very harsh radiation, harsh environment which these detectors are going to follow. So I'm showing an example that in the CMS we are using cathode strip chambers, CSCs. If you see, the efficiency is going down. So if we use the first station of the gem, we can recover the efficiency. So the advantage of gem is that as soon as our detector, the old legacy detectors are dying out with the time, we can recover our performance using the modern gem detectors. So that's why we are motivated enough to use gem detectors in the CMS experiment. And also in the right plots, we can see that there is a effect on the momentum resolution. So momentum resolution is improved. Okay, so this is the motivation to use gems for the future. So we are adding layers of gems in the, you can see the red colors in the bottom picture. We have G11, we have G21, we have ME0. These three stations will be upgraded in the CMS experiment using the gems. So these green colors, if you see, these are the legacy, the old detectors we have. And I have shown an example where the old detectors are performing not on that, on that grade actually. So their efficiency is going down, their performance is going down. So we are adding some layers of these gem detectors to recover the efficiency. So now they are, as I said, that with the time, the aging and discharge problem will occur, and this will make our detector inefficient. So what we will do is that we will check that this detector can, stay longer, can work longer. So what we do is that we can do some test on these detectors, that how long these detectors can stay. So if you see the CMS requirements, we are very above than that we have checked these detectors to this much of the charge. So this is much, the CMS criteria that our detector should pass 5 times the required charge they are going to face in the coming 20 years or so. So that then we will compare the timing resolution, we compare the angular resolution. So in every sense, the detector which we choose is going to work because it passes the criteria and they are above the level than the requirements. Now, how do we produce these detectors? So I start with this thing. So if you see the structure, we have a very small thickness. The sample thickness is very small. We have 50 micron of kapton, and on kapton we have a kapton or polyimide or apical. So we call it as, say, polyimide. So you have a 50 micron polyimide, and on top of it we have a 5 micron copper, and in the bottom also we have 5 micron copper. So it is the conducting surface on which we can apply the voltage. So these, since you can see that these are very microscopic scales, so we can use the photolithographic technique to produce such sensors. So the fabrication involves the photolithographic techniques. So if you see, we can use the double wash technology where we have the raw sample, and on raw sample we can use photoresist and masking and etch the polyimide to produce these holes. Now why we need these holes? These holes are single proportional counters. So if you have to create a field in which you can create an avalanche after the primary ionization happens in the gas volume. So these single proportional counters will give me enough charge after the avalanche so that I can see the particle interaction. So this avalanche is happening inside this hole. So this whole field is crucial for us to have the interaction. So this whole is, if you see, this is 50 micron, here it is 70 micron, bottom also we have a 70 micron. So we produce the sensor samples, the gem foil samples, using the double mask technology if we require just say 30 centimeter by 30 centimeter or 40 centimeter by 40 centimeter. As soon as we go for large volumes, so in CMS we require at least 1.5 meters. So we We cannot align these two masks in the photolithography technique. So we use a single mask technology. And you can see that most of the steps are done only using the single mask. To master this technology, it takes around 4 to 5 years. Because it's a large sample, single mask technology is not easy to understand. So our companies are taking time to understand this particular technology when they have to produce large gem foil samples. Okay, so this is the actual image of the gem foil. So you can see that, as I have told, that this is the cross-sectional view where you can see the inner hole, the outer holes. So then there is a layer of the holes. And you can see the top layer of the single mask foil. You can see the bottom layer of the single mask foil. And you can see the difference in the etching also. The bottom layer is not that good etched. And the hole size will also differ. There is a difference of 20%. But after all, when you see the effect on the gem performance, it is not much. Which is really a good thing with this detector. Now, so you have a gem foil, you can build a detector, you have electrodes, and you have a gem foil. So you can build a single gap detector, single gas gap detector. But if you need a large gain, so you prefer that double gem or triple gem detector. Alice is using a 4-stage detector. We are using the 3-stage detector because of our requirements. As soon as you are increasing the layers of the detectors, you can see that you are increasing the amplification layers in the detector. So your first gem will give you a gain of say 10 raised to power 1 or 2, and then you multiply. As soon as you increase the layers, you get the more gain and more charge. When you go to the microscopy scales, the detector output in terms of charge is very, very less. So if you amplify it considerably, your thresholds for the front end to pick up is considerably fine. So it depends on how much threshold your ASIC can handle. So it is important that your natural amplification inside the detector is very, very large. And also it helps in the signal to noise ratio. So we have chosen a triple jump technology because gain is large. And also the operating voltage is very, very less. And if you see the discharge probability, it is comparably very, very less. So for higher gains, for reduced ions backflow, we want to avoid the ions because they can slow the detector, the time resolution can be worse, and they can initiate more other degrading effects. So, and also the discharge probability. So due to this, we are not using the single foil layer, we are using the 3 foil layers for making the gem detector in the CMS experiment. So as I have told you, we have 2 electrodes. One is cathode, another one is anode, and we have 3 layers of gem: gem 1, gem 2, gem 3. Your particle enters, it produces the ionization, and your charges are amplified using the avalanches, and your charge is amplified. Electrons will go forward. The field is chosen in such a way, and ions will go backward. So ions will be either absorbed by the copper present, 5 micron copper present on the coils, or at the most they can be captured by the cathode surface because we have copper here. And similarly, in the second stage, you have the more amplification, and also in the third stage, you have more amplification. So gain is going high. You multiply the gain, and at the last, you induce the signal on the PCB strips. So your strips are engraved in the PCB board, and then you have a front-end electrons to pick up the signal. So this is our detector. You have a meter by half, and you have different sectors. So you have different ASICs who will sit here to pick up the detector readout. So I have explained that this is the CMS detector, which is a big detector. We use the single mask technology to produce the gem foils. We use not only single but triple stage detector, 3 foils, to have the gain of the order of 10 to the power 4 to 10 to the power 5. Now, so CMS Gem decided to go for this technology, and now we have to produce these detectors. So CMS has to produce 144 detectors, and if you add spares, 16 spares, then it is 160 detectors we have to produce. Now with the timeline, we cannot produce a detectors at the one site, there are a lot of issues involved, because you have seen that these are very, very delicate, and the microscope technologies are in microscopic technologies are taking place. There are many, many things involved in the process. So you divide the job. So CERN is the central site and divided the jobs to these 5 peripheral sites. So India is one of them. So we have to produce detectors, test them in the labs, and also after testing them, if they are good, they are being sent to CERN. Their further commissioning will happen, and then they will be installed. So this is the story, say, of 2017 or so. So we started with the production. So we have the material to prepare for the assembly of the detector. So we do the preparation of the readout boards. We have to prepare the electrodes, which are PCB based. So we prepare the boards. We put the we fix the gas connectors. We prepare the drift boards. In the drift boards, we use the SMD components in the sidelines. So handling of these SMD components is very, very tricky. So we use tweezers and valve stations. So students are handling these jobs quite well. They are also assisted by engineers. So for all these processes, a day, minimum 1 day is required. Then we go for assembly and stack preparation, stack of 3 foils along with the 2 electrodes. So we go to the clean room, class 100, and we try to do the assembly of these detectors. So you can see that there are different steps involved, and we prepare a detector. In the bottom, you can see both the two students are handling a detector. So we have prepared a detector, fabricated a detector, and it took almost 4 to 5 hours in a clean room. So it is also a very, very delicate process, because if any dust particle enters into the gas volume, it will create discharges, and then the detector will not qualify for its use. Then we have the quality control results. So we have the first quality control. The first quality control for any gas detector is the leakage of the gas, if there is any leakage. So we powered up the detector. We pressurize the gas up to 25 millibar, and in 1 hour we noticed that it should not be leaking too much. At least it should be within the limits, and limits are 7 millibar per hour. And we see that all the 16 detectors which we fabricated in India have passed this criteria. So these are the actual results. The second is the VI, to know the leakage current of the detector. The third is the spurious rate. So when we supply the carbon dioxide, it is not the ionization medium at that point. So we see that there is no signal we should read out. We should not have any signal. We should not have any interaction inside the volume. But since we are using screws to tighten the sidelines, so we can see some discharges happening at very, very high voltages. So 1000 microamp roughly means 5 kilovolts. So at that point, you can see discharges, and this has to be minimum, at least minimum background rate expected at the CMS experiment. So our operational current will be very, very low. So the rate is very, very low, but we tested this detector to see many stringent conditions we can apply. And other one is the effective gain. This is the actual measurement of the gain we do using the X-ray source, and we found that all these detectors have 10⁴ to 10⁵ gain at 7500 microamps, so bias voltage of say 3600, 3700 volts. And since we have the different sectors in the detector, so we can see that the response uniformity with the, if we have 24 sectors, then we can see that the response uniformity, the gain uniformity, the gain is varying within 15% in all these sectors. And then these guys are happy after producing these detectors, because these detectors are ready for the shipment. So the detectors are packed and sent to CERN. At Punjab University, we produced 8 chambers. At Delhi University, we produced 8 chambers. And we tested Punjab University chambers for gain and uniformity studies. So in all, we sent 16 detectors from India. 7 detectors were assembled at CERN while training. So we have produced 23 detectors from Indian commitment. You can see other sites as well. So in total, we finished this production in the year 2019. Now these detectors are also tested after the shipment, because you have to see for any damage or other things. Then these are you have to put the electronics on this. So you put the S6 FPGAs, and then these detectors are being installed in the CMS. We have also already installed the first end cap, and second end cap is going to be installed next month. But all the detectors are good, all of qualified the criteria, and this is the good news for our production site. Now, this is the crucial part. If we do this exercise, what we gain for our Indian community, with the help of our industry, we can produce these gem detectors. So we have to initiate some transfer of technology from CERN, because CERN has the patent. So CERN and Micropack, along with BRC, signed this TO2, and then we started producing these foil samples. First of all, they produced 10 by 10 samples. We measure the leakage current, we measure the we did perform the optical studies on the holes, we performed the electrical characterizations, and then we went for the large scale production. So we have to qualify these foils so that these foils can be used for any indigenous or any LSC upgrade experiments. So first of all, we produce 10 by 10 sample. It is the active area you can see, and this is the actual SEM image we have for the holes. So this single foil has to be first of all tested through the optical measurements. We did the optical characterization of these samples. You can see that the inner diameter is expected to be 50 micron, and that's what we are getting here within the errors. And the outer diameter is 70 microns. So we measured for all the foils, all the 3 foils, and we found that the average diameter is 50 micron and the outer diameter is 70 micron. So we measured the diameter, but this is double mask for the moment. So we measured the accurate 70 micron and 50 micron holes dimensions. Then, is there any etching defects there? So we found that during the optical studies, we found some unetched samples, unetched holes, undersized holes, oversized hole, the foil without hole. There is excess etching, there is burnt. So we found some effects. But these effects are very, very common in any foil because you are producing so many holes. So out of, say, 0.6 million holes, you have just hundreds of defects in the kapton and few in the copper etching. So we did this study and compare these studies with the CERN-produced foils, and we found that our foils were performing better. Then we did the electric regulation, basically the leakage current. So at 500 volts, we should have 1 nanoamp leakage current, and that's what we found for all the foils. Similarly, it changes with the humidity. So at the different humidity, we tested and we found the same result as we have seen for the CERN foils. So the 10 by 10 foil samples are pretty good. Then we also did the spark study, the discharge study of these foils, and for this we have to supply the nitrogen, and then we have to see, after applying the voltage, we have to see if any discharges are happening. We found that only one discharge observed at the voltage of 600 volts, which is expected, and at the relative humidity of 70%, which is we have tested the CERN foils also. So the all these studies show that the criteria which we have chosen is same for CERN and is same for the Micropack foils, and both foils are behaving normal. Then we built the detector. So again, we have to build a 3-stage detector because we were targeting the CMS gem upgrade using these foils for the years to come. So what we did is we assembled this detector and we performed some tests on these detectors. So the first test is again the leakage current, and we went to 500, 4900, so approximately 5 kV volts, and we found that the behavior is ohmic. And then we also measured the spurious signal rate, which is well without 1 Hertz for the 10 by 10 detector, and this is pretty good. And then we measured the MC spectrum using the X-ray, and the last one is the gain. The gain is the important test. We have to see this is going to work in the region where we have very, very harsh environments. The rate is very, very, we need very high, rate detector. So we are seeing here that it can handle up to 4 kilohertz, and the gain is 10 to 4, 10 to 5. And also the CERN detector, which is 10 by 10, if we assemble the detector using the CERN foils, the response is same. So we saw that this results were pretty promising. So we went for advanced tests, which are hysteresis effect, polarization effect, the reevocability. This is due to the charging effects, charging up effect, or the polarization effects happening in the Kapton material. This is pretty expected. So with these advanced tests, we went to qualify the detector, and 10 centimeter by 10 centimeter were qualified, I think 2 years back. And then there are, in fact, the CERN is also purchasing 10 by 10 foils from India to do some small stage experiments with the foils. So 10 by 10 samples, anybody can go to Micropack and get those foils. These are double mask foils. So anybody can use and make the detector. There is no issue. Even in fact, they can also give you a drift board, readout board. So anybody can do 10 by 10 centimeter detector. Then we went for a 30 centimeter by 30 centimeter. There is the same story with the 30 by centimeter. There is nothing new. We produced the foil, we made the detector, we tested the leakage current, we assembled the detector, we did the gain studies, the rate studies, and the uniformity studies. So detector is performing well for the 30 by 30 also. Now the crucial thing is that as soon as we will go for a large size production, we have to, we also did some other tests on these foils. So we did the charging of effect test. So here you can see that there is the increase of the gain for a moment, but it's stabilizing. So the bottom line is that as soon as you have to use the jam detector, you have to ramp up for a while, say 2 hours or 3 hours, and then it is ready for the use. So there are some kept on, effects which happens to come in the play. The right probability is about the discharge probability. We use the alpha source, americium 241. The americium source gives us 100 times more ionization than the MIP. So we can do more ionization inside the gas volume, and we can see that up to 10 to the power 9, we got no discharges in the detector. And in the CMS region, if you see the gain, if you compare with the gain, then there is only one discharge happening in 10 to the 12 interaction. So we are far away from any discharge. So discharge probability is very low. So detectors which we are using is having low discharges. So this is very good news for us that any detectors are also having the low discharge probabilities. Then we went for the large size foil production. For the CMS experiment or any LSC upgrade, we list large size, and it has to be single mask technology because double mask technology cannot handle the mask alignment above 40 centimeter or so. So we produced large size gem foils at Micropack. These are the actual images of those foils. And then in the clean room, we did the leakage current measurements. This was pretty good foils, and we went to assemble a detector. So this is actual CMS style chamber, which is going to be used in next upgrade. So upgrade down the line may be happening in a year or so because of Corona thing. The things are delayed a little bit, and we assembled this detector and tested for all the measurements. We found that the detector is performing well, but there are small issues, and we are expecting a next samples from Micropack to see more improvement in these foils. And as soon as we will get the foils, we will test those foils, and if they pass, they can be used in CMS experiment in the future. So apart from this, we have tried to see the applications using these detectors. So if you use any photon, gamma ray photon, X-ray photon, it interacts with the material and it loses energy. If you lose this energy and convert this into any electrical signal, you can make an image of this. Because this is a proportional detector, you can always you have the proportionality of the effect. So we have the setup where we have the X-ray source as the main photon source, and we have the 10 by 10 detector made using the Indian foils, and we have a front end, and front end is powered using the low voltage supplies. So the X-ray will go there and interact with these metallic components, and we'll have energy loss, and that energy loss will be captured by our is equivalent to the ionization we will see inside the detector. So we produce the image. So this is the actual image. We are having very low number of events here, 1,000 events, I guess. We can increase the number of events. We can. This is the first detector, so we can use more clean foils, so the resolution can go up. But the proof of principle is there. So we can use these files for any applications, for medical imaging, for astrophysical applications, for whatever uses a community wants in nuclear and high energy physics. So a micropack can give you files and also the complete detector components. Even they can also help in assembly, and you can use these detectors for any applications you want. Okay, we have produced very nice, good quality gem detectors for the CMS experiment. We were a production site, and we produced 23 detectors. We are ready for next assignment in the second station and also the zero layer. Any industry is also producing good quality gem foils. We can use them for any application. They can be used in astroparticle or radiation detection applications. And most important thing is that gem detector uses eco-friendly mixtures of argon and CO2. So we need not to worry about any freon component or any global warming potential high index gases, because they are banned in any uses, at least in Europe and also in India now. The main work of this talk is incorporated in these two theses and also in these NIM and JINS papers. Ashok is a postdoc in University of London, and Ariel is going to work on pixel sensors in Atlas. And Mohit has recently got detector award in CMS collaboration. It is his award. So the hard work which I am showing is from the students' work in the lab, and community has recognized their contribution. And also this is the big group where me and Naeem are the faculty members, and there are engineers, students, and technicians who are helping us to finish the job. Thank you very much.
Okay, thank you very much, Ashok, for your nice presentation where you summarized quite well the detector, of course, gem in general, but also more specifically your own groups and universities efforts, including trying to kind of make the gem foils, which are the main components locally, and also qualifying them and in a way proving that they are as good as the foils that you have been receiving from CERN and other places. So that's very interesting work. And so, of course, congratulations on behalf of all of us, and also all the best for your future activities, in trying to, of course, make more counters, but at the same time, also trying to find applications in the Indian context. Okay. So with that, let me then open the colloquium for questions from the participants. If any of you on the Zoom, if you have want to ask a question, please raise your hand from the Zoom platform, or you can just unmute your mic and then ask the question. And those of you who are on the YouTube, please type your questions at the chat box. Yeah.
First question.
Yeah. Yes, sir.
How do you align these over 3 foils which are at a distance?
Okay, so the gas volume is inside the spacers. So spacers are made up of FR4 material. So these spacers are first of all, we attach the foils to the spacers. So we have the foil, and we cannot paste, but we cannot, we can screw the foils to the spacers. For example, we can glue it. For example, we glue the foils to the spacers. Just an example. So we have a foil. So you glue all these 3 foils after proper stretching. So you do the stretching using a jig. So there is a mechanical jig which does the stretching for a day, and you paste the spacer. So there is say 2 mm spacer. Okay. Now you do the job for all the 3 foils. Now you have 3 foils. Now those spacers have the screw holes. So you always can, when you put the drift and the cathode and the anode, you can always put the screws for the 10 by 10 and 30 by 30 samples. But if you go for a CMS style foil, there also the gas volume is, contained inside the FR4 material spacer. So
no, I was talking about the factory making time when you put foils one above the other and do lithography printing, and then you do the etching. See, each individual foil is etched separately. So now you have a set of independent foil which you have to align.
So single hole is so in the triple stage reactor or in any, even in the single foil, you have not only the single hole contribution, it is the contribution of many holes to the avalanche. So even if they are not, perfectly aligned, it is not needed.
Okay, thank you.
Yeah.
What is the size of this 10 micron hole it is or what?
70 micron.
70.
70 micron hole.
Yeah.
Okay, right. So,
Rajnish, do you have a question or? It doesn't have. Okay. Ashok, I want to ask again on the, can you little bit elaborate on the single and double mask, the pros and cons, and if you can, maybe I missed some part of it.
Yeah.
Yeah.
So in the double mask, it is very easy process. So in the double mask, you have the mask and you have the mask at the top and mask at the bottom.
Correct.
So you can etch the hole very easily.
Yeah.
You can etch the copper and you can etch the polyimide easily. But it can, the upper mask and the lower mask, since it has the micron geometries, the hole pitch is 140 micron. The size of the hole, the outer size of the hole is 70 micron. So we are in the micron. So to handle this alignment. Here we know. So alignment, you can, industry can go up to 40 centimeter only. So to have this foil more than 40 centimeters, say 1 meter by half meter, you have to use the single mask technology. Okay. And single mask technology, the single mask is helping in lot of etching, which is a difficult process. Nobody, I have written here, but nobody knows the actual thing which industry is doing. So Korea took almost 5 years to stabilize this process. Now they are supplying the foils for the CMS experiment. Micropack is trying for this technology since last 1 year or so. We are helping them, but still, a lot of work is needed, and it will take, another year or so to stabilize the process. We have got few samples, but those samples are having small issues. So I'm hopeful that they can do it, but this is a process that industry has to master. People in the industry has to master. So it is just the large size you have to go for a single mask technology. The small detectors you can produce. So that's why I told you that double mask foils up to 30 centimeter you can get from Micropack, and they are very, very nice foils.
So what is the material of the mask?
Oh, I forgot. I forgot.
Okay. And obviously the shape of the cutout is important. This kind of a conical part, you have the minimum distance at the middle and tapering off, etc. Probably for the field, discharges. And,
exactly.
No, but that actually comes automatically through the etching, because you cannot etch straight through, and etching is always conical. This is old cosmic ray etching detectors, Electron. The shape you can, if you want to make square, it is not possible.
I see.
Yeah, this is how, because etching, the flow of etching through the Electron or any polyimide is a conical etching, because the ionization which gets, when you etch slowly, it is the middle point which etches first, and then it progresses to the sides.
I see. Okay. Ashok, you are saying something? No.
No, it's
Okay.
fine.
Okay.
Answer is
And
fine.
I also want to ask in the next slide, I think probably you have here. So I think that one is top and bottom.
Yeah.
And the cross section of the holes, they seem a little distinct.
20%. There is a variation of 20%. So,
okay.
so I told you that one of the students has worked on this issue actually. So you have foils with the asymmetric holes. So upper size is different, lower size is different. So a student is also connected actually. Ashok has worked on the gem detector where he arranges these foils in a symmetric way and non-symmetric way, all the combinations he tried.
Okay.
Then you see the performance of the detector.
These are double side.
Yeah. So
these are double side etching ones or single side etching ones?
Single side.
Single side etching ones. Yeah. Okay. Yeah. So
the performance doesn't change.
Doesn't change. Okay. But since that close to the hole, you actually have copper foil. The fact that whether you should keep a definite annular surface area which is etched away, is that a good point because it will reduce the discharge?
Sure. You're right.
Okay.
You're right. Okay. So what we do is in the single mask, since we are using single mask, so our triple stage give you a gain of 10⁵, but we operate at gain of 10⁵ or lower.
Okay.
Yeah.
So you go for lower voltage, that means.
Yes. The operating, we have tested up to 1000 microamps, but we operate at say 600 microamps.
Actually, the individual foil is working at very low voltages. So it's like 450 volts per foil, the potential difference between top and bottom layer. So it's far below discharges for a single layer gem.
Okay. Ashok, I have a couple of more questions. One is on the image that you shown towards the end somewhere, and it's very
medical imaging.
Medical, yeah. I think you image some keys or whatever.
Yeah.
So, how do one read this image? Like, what is this very high counting that one sees in the like those blobs, red ones?
Okay. So first of all, if you see the line, we have some dead strips or so. Another thing is that
that is that vertical line.
Yeah.
Okay.
And these red points, say they are very, very high. This can be this is not the material we have put, but yeah, we have to understand what is this happening there. But sure, we have just we haven't got sure that the detector we are using is of the utmost quality. So what we do in the second iteration is that we will make a very nice detector, and again we will do this thing. But frankly speaking, we do not know what is these very, very high energy events, because we have to understand, is it the electronics noise or is it the detector component? Most probably it is the electronics noise, but for the moment we do not know, because for the moment this is the first triple detector we have made here. So we do not know that it is a detector component. So we have to separate the components, either detector, software, or electronics. So we cannot say that which part is contributing.
So this could be actually some of your dirt has gone in, and you have a nanoampere level discharge between the surfaces.
Sure.
Actually, you can say it's a kind of hot pixels, so which are
So hot pixels, how do you create? That is because your clean room characteristics.
Possible.
It's also dependent upon the flatness of the foil or the local discharges occurring inside.
That you can do it by you go 50 volt less, and if they disappear from these points, you can it will happen that you just reduce the voltage on the foil, and then what you get red should disappear.
Yeah, so little playing with the tuning of the parameters as well as the components can figure it out what is happening here.
Another question, sorry, I mean, if there are others, please raise your hand. So I'm engaging the speaker with more questions, but please ask your questions. So this is regarding the timing of the detector, about which, of course, one of the main factor, I guess, is your gas mixture.
Yeah.
So while it is very nice that you said that you try to avoid, let us say freon-based gas mixtures and so on, and it's very nice also to use more eco-friendly gases. But maybe this kind of resolutions that you showed is good enough for CMS.
You can improve by
I think you talked about 6-7 nanoseconds, right?
Yeah.
Okay. Somewhere very beginning, I guess.
Yeah.
Here it is.
Yeah, you have a CF4.
Yeah, so that is 4.5, 4 to 5, and but argon CO2 with no CF4 is more like 7 to 8 nanoseconds.
Yeah, sure. So we are avoiding CF4, so timing is going bad. Yeah, sure.
Yeah, but your CMS requirement says less than 10 nanoseconds. So this is it's okay. But my point is that if you were to use this for even like you said, medical applications and so on, sometimes it's also important apart from just the position. If you also have a good timing, it actually helps further reconstruction.
Yeah.
Is there a
So then we will not use these gems. So there is another technology, fast timing gems. So there is a very varied class of gems. So if you go for a timing, you will not produce holes only, not only holes, but you can produce a mesh of the mesh, a kind of a structure, different structures in the microscopic scale, micromegas, or you can use a fast timing gem detector where the ions, you cannot use the 3-stage detector, you use a single stage detector, and you have a hole, kind of a hole or a kind of the hole or something, but surrounding areas you have a strip where you can collect the ions. Okay, so you have to catch hold of the ions immediately. So there is a different technology where fast timing measurements are done, and you can reach up to 1 nanoseconds or so.
Can I ask another question if you don't mind?
Yes, sir.
Have you attempted with the CO2 percentage less instead of this 30 and 15?
So those studies are already done. I am not including. I have not included those studies. But if you increase the CO2 to different level, then the characteristic changes, changes. But timing, since timing is not that much important for us, but if it is important for any other people, then they surely can change the gas mixture, or they can go to the next class of gems, and that is also possible in micro pack, because double mask in the small size is possible. Any structure is possible.
I think with gem, so it's not only time resolution. Another good thing is gain. So I think with triple gem structure, you can get the best gain and the resolution, timing resolution of 7 to 8 nanoseconds with these gases. If you change gases, either you lose gain or timing. So that is the best configuration that is chosen by LSCB and then opted by CMS for this purpose only.
Ashok, there's a question from Professor Acharya.
Yeah, sure.
Yeah, hi Ashok.
Yeah. Hi.
Yeah, this Bangalore company, which they had the agreement with the CERN, does it mean that they can supply to only CERN, or any other experiment or any other geometry they can make foil?
No, any experiment or anybody they can supply. There is no issue at all.
Okay.
Yeah.
They don't need to get permission from CERN or anything like that.
No. In fact, they are looking for the vendors for the purchase.
Yeah.
But you have to provide the Gerber file, because they don't produce Gerber file by themselves. So you have to provide the Gerber file, what kind of a foil you want to make.
If you want to produce another structure, so then they just need the Gerber file of the structure, which is produced by TCAD simulations. So if you provide the Gerber file, they can give you another kind of a foil, a new kind of a foil. But if you need the same files, this Gerber is with them, so they can immediately.
Yeah. Okay. Yeah. Thank you.
Sorry, one more question on the very first slide and the very first point that you brought about. Very interesting image of a miniature painting that you showed of. How do you get some kind of this color or spectroscopy? I mean, I don't know what it is. How do you get this third dimension?
Just wait. Yeah, I have some details. Okay. So you have energy resolved X-ray.
Yeah, spectroscopy.
So what they do is they try to see different elements.
Okay.
So as soon as you have different elements, okay, in the X-ray fluorescence, they try to see the fluorescent image and having the different elemental compositions, and they rebuild.
No, but this is with gem, you said.
Yeah, so the XRF, the fluorescence is measured by gem.
Fluorescence is measured by gem.
Yeah. So you put X-ray on the sample and you see the output through the gem. So resolution is very nice. Position resolution.
Energy resolution.
So that energy resolution improves if you use less CO2. That's the reason I was trying to say.
So here,
use gain.
Yeah, here they have used the CF4 also because
they have to.
Yeah. So
CF4 will be needed because otherwise you don't get so much gain.
Yeah.
But then
CF4 actually the gain comes down.
No, but in CF4, yes, gain comes down with the particular voltage. Then you have to go to higher voltage to get the same gain as compared to argon CO2 if you use CF4 as well. So you have to apply more voltages to reach the higher gain.
Yeah. For same voltage, CF4 gives lower gain compared.
Yeah.
Yes, exactly.
Yeah. For same voltage, you will get less.
Yeah.
Okay. So, I see. So you kind of do a spectroscopy kind of thing.
So main aim is the gem to reduce the discharge probability that was measured in MSGC just before gem. So
actually, I wanted to get hold of more details, but in his talk, he had just shown this slide. That's all, and nothing else. So I wanted to see his paper, but he didn't mention. So this was the only thing which he, just flashed in the slides and then went away. So I saw that in 2015. At least he has shown this slide in his talk, and it is available. It is freely available on the
trade secret. How it is.
Yeah.
Okay. Okay. Any more questions from the participants? Okay. So if not, once again, let us thank Ashok for his excellent colloquium and also bringing up this nice kind of activity towards the end, mostly talking about the indigenous developments of these gem foils production in India, and also happy to know that Micropack is authorized or allowed to supply these materials to the Indian scientific community. And I think that's very nice arrangement. So with that, thank you, Ashok, for your nice talk.
Thank you. Thank you.
All the best for your future endeavors in this.
Thank you.
Thank you. Thank you, everybody.